Um, Hello, everyone. Yeah, my name is Nick Scholand, and I'm from the from Martin Lukas Group in Göttingen, Germany. And yeah, it's my pleasure today to present this simulated tubes phantom we now have in BART, starting with version 7. And yeah, um, thank you, John, for already sending the my binder links into the chat. If you are on the basic BART webinars GitHub page, you can just find it here. You just need to click on this button. Okay, good. Yeah, what's the outline for this talk? So we want to start with creating a Cartesian image space phantom, or Cartesian image space phantom with a signal development and with various contrasts. And because it's pretty straightforward, you can do this at the binder or locally later to create a k-space phantom from this in a Cartesian style. We will directly go over to non-Cartesian k-space phantoms. And yeah, so to run this notebook, you have to, again, as also Volker showed already, you need to have a helper function for showing images and helper function for visualizing time series and values from this time series. Yeah, as I mentioned, you need BART version 7 for this. And now let's come to the basic concept. So the basic concept of this simulated tubes phantom is that we have splitting between the geometric components and the signal components. So you can see a visualization of these geometric components here on the left. And for each of those components, we need to create a signal component. This is really nice because you do not have to simulate a signal for example, a pixel with the same relaxation constant combination again. So you assume that each of your components has a homogeneous T1 and T2 value, and therefore you just need to create one simulation for this. In this example, we would just need to have 4 simulations, and we would directly get our final result and our signal and our contrast change in time. Okay, yeah, the basic idea is this geometric components. These geometric components, we will start with the Cartesian one in image space. And in principle, because the Fourier transformation is a linear operation, linear transformation, we can just apply this also to the Fourier space. So we will then create those individual components in Fourier space. And our final signal after multiplication with each of these components together is also still just the sum over all of these components. You will see it applied later. The cool thing also with this setup is that you are completely independent of, for example, how you do generate your signal. So sure, we have a BART and option to create those signals. We will see this also in the following. But in principle, if you just follow the rule of having as many signals as you have geometric components, and you can store them in one of these CFL or BART compatible files, and it's in the correct dimension. We will also see this later. You can use any tool to create those signals, simulations as you wish. And then you can just multiply it, sum over this component dimension or coefficient dimension, and you will get your final simulation. Okay, so let's start with the practical part. In the beginning, we just need to define some basic numbers. So here we have our samples. So we want to have 192 samples for the pixel-wise phantom. And also, this is important, the tubes phantom in BART, which can be composed or decomposed into this individual core components, has 11 tubes. So you always need to have 11 signals to create this phantom. As John already mentioned, you can use the -h flag for each of those tools to have a look of how it, or what it does. Here we have a look at the phantom tool because this is what creates us our geometric components. And we can see that the tubes phantom has this -t flag. By the way, you can see my mouse, right?
Yeah, we can see it.
Okay, awesome. Right, so the -t flag and the tubes phantom has this additional option that you can split it into this component. So we need -t and -b to create those geometric components. We can, or you can run this cell easily with this head -n. We print out the first two lines of the header file, which includes in the BART format always the dimensions. So we can see we have our pixelized 2D phantom here in the, or actually, yeah, the phantom with these 192 samples. And we have also in this sixth coefficient dimension, the 11 components of our object. To visualize these components, we can reshape these dimensions a bit. If you want to know details about it, just ask later. But the final result is that we can see all of those components. So we have one large background component, and then 10 individual tubes here. Yeah, so these are the components. Now let's go over to how to generate a signal. As I mentioned, you can use any tool, also any non-BART tool to it. You just need to have to store the signals later in the BART format. But in the following, I will just show you how you could use the signal tool in BART for this. And the signal tool, if we again have a look at the help output, we can see that there are a lot of different options, especially or mostly analytical signals for various sequences. For this tutorial, we decided to use a flash sequence, and we want to have an inversion recovery preparation. We can also pass information about the repetition time with this -r flag. We can pass the number of repetitions with this -n. And also, we somehow need to pass information about our relaxation parameters. For T1, this is implemented using the -1 flag. Then you define a minimum value and a maximum value and a number of T1 values which should be simulated here. The same holds for T2, just with the -2 flag. Have in mind, we will see it later, but if you, for example, choose 3 T1 values and 3 T2 values, it will always simulate all possible combinations. So you will end up with 9 different signals. But yeah, let's start with a very simple simulation. We want to simulate the signal for water at 3 Tesla. Therefore, we pass the T1 and T2 value, we pass the number of repetitions we want, we pass the TR, and we say we just want to have one simulation. For this notation with this min and max, we would now just add the T1 time because we do not need any range here, and add the number of simulations for T1 and for T2. And we can print out the result, which just shows 400 time steps, which is what we defined here. So we now have one signal for water at 3 Tesla. But as you have seen before, we need 11 signals to multiply it with these geometric components. Therefore, we want to simulate now a range of various T1 and T2 combinations. These, I will just call it component of tubes. Just start with a minimum T1 of 0.5 seconds up to 2 seconds. We want to have 3 different combinations of T1 and also 3 different combinations of T2. And the result is shown here. So all the combinations of T1 are actually stored in the coefficient dimension 1, so in the 6th one. And all the combinations of T2 are kind of stored in the 7th dimension, coefficient dimension 2 in BART. As you have seen before, all those components of the phantom are actually placed in the 6th component, 6th dimension. And to be able to multiply them later, we need to concentrate all those signals in this coefficient dimension 1. This can be done by a reshape command. And afterwards, we can see that those tubes, we have 9 different signals for these 400 repetitions. Good, because we have these 11 elements in the tubes phantom, we can now stack them together to get 11 elements. I decided to choose the water background, then all these tubes combinations are stacked on top of it, followed by a water tube again. And this is our computed or our simulated signal component. The actual combination of the geometric component and the analytical component or the signal component is then just a multiplication. So you have the geometry, you have the signal, multiply them, and with this minus s and the dimension you just sum up over the coefficient dimension 1, which is the 6th dimension. And this will end up in a phantom, as you can see. So we have our samples or our 2D image in the first dimensions again. And this is then present as, or we can follow it over 400 repetitions, so time steps. You can also visualize this, and we can see nicely this is decreasing and increasing contrast again for these various tubes. Yeah, so this is how you would create a Cartesian image space phantom. The K-space phantom, for those who are following this tutorial, you can just add a minus K to this basis create or geometric basis creation command, this phantom command, and you will end up with a Cartesian K-space phantom. And because this is kind of very simple and you can easily do it, we decided to just directly go over to non-Cartesian K-space phantoms, and therefore I now want to show you how to create a radial non-Cartesian or radial phantom. And yeah, the key here is that we have a trajectory. So the information about this non-Cartesianness is splitted in BART. In the first part is the trajectory, which stores the location of all your samples, and the second part are then actually your data and these samples. So we need to create this trajectory first. We want to have a two-fold oversampling. And so we have a number of samples, we have a number of spokes, and we pass the minus R for a radial sampling here. We need to scale our trajectory to ensure this two-fold oversampling. And if we have a look at the dimensions of the resulting trajectory, we can see this BART internal 3 in the beginning. This is for non-Cartesian important because this just stores the information in X, Y, and Z. In X, Y, and Z, and that's why it's a 3. These components are then stored for each of these 192 samples and for all of the 95 spokes. To create this geometric basis or this geometric components here, that's pretty simple. You want to have a Cartesian geometry or geometric component, so we just pass the minus K. And we also need to pass the information about the position of the samples. This is this minus T, which allows to pass a trajectory. And the resulting geometric components have this 1 in the first dimension, which says it doesn't have information where the samples are, but it stores the information of how these or the value of those sample points along this trajectory. So here you can see the splitting into location, where those samples are, and what those sample points actually have for value. To combine these informations, we can, for example, perform a non-uniform FFT, an inverse one, we pass the dimension of our samples here, and this is done to reduce the effect of this oversampling. And we pass the information of our trajectory so that we know where these samples are. We pass the values of these sample points with our data, and we can have a look at the results by reshaping it again. And we can see those individual components here. So if you do this in Binder, this NUFFT might take 30 seconds, so be patient, but you will see those images afterwards. Locally, it should be quite fast. Yeah, to visualize this now, we can create this phantom again by just multiplying these geometric components with our signal we previously used already for the pixel-wise case, and just sum over the coefficient dimension. I do this here for the projection of our non-Cartesian data into the pixel domain. So I will do this on the output of the NUFFT so that it's nicer to see. But you can directly also do it on the case space itself. And if we visualize the time evolution of this, we can see the same as we saw it before, just that we do not here have this blockiness in the borders, and we have some ringing artifacts which come through the truncation of the case space. We can also compare both phantoms. So here the time step 100 is sliced out of the pixel-wisely created phantom, and the case space phantom, which is transformed into pixel domain. And you can directly see these differences, why this is in pixel domain and why this is in case space. And to summarize this, the basic concept is pretty cool and pretty generic. So you really have this split between geometric components and signal components, and this gives you the freedom to, on the one hand, create signals with any tool you want, but also it allows for very efficient computation, because if you, for example, would go through this pixel-wise phantom, through this pixel phantom, pixel-wisely, you would simulate, if you want to simulate each pixel, it might take a lot of redundant simulations for the same set of relaxation parameters. So you really can ensure that for each set of relaxation parameters, you just have one simulation done, which makes it pretty fast to do this. Yeah, then it's also really easy to do or create case space phantoms, because instead of just using the ellipses in this pixel domain, you just use the Fourier representation of it. And for BART, it just means you add a minus k. So that's really easy. And also to do or use non-Cartesian phantoms, it's also very handy, because you just need to pass your trajectory. And also this trajectory can be created with other tools. So if the trajectory tool in BART doesn't provide the trajectory yet you want to use, then you could just create it with an external tool, store it in the same dimensions with this x, y, z in the beginning and samples and so on. And you could also just directly use it for creating this phantom. And with this, I'm done with this tutorial. If you have any questions, feel free to ask. I see there are already some in the chat. I will have a look into them. But also just speak up if you want to. So the first question, okay.
Oh, go ahead, Nick. Sorry, didn't mean to cut you.
Yeah, sorry. Yeah, the first question is there a parameter in the signal tool to change the field strength? Actually, I think there is none yet. You simply could have a look. So right now the signal tool provides analytical expressions. So if you have parameters in the present analytical expressions which can be changed and which are hard-coded, you can simply make them accessible by the command line. But in principle, I think there's no default option here. It depends on the signal model which is used, and you can need to have a look there. But yeah, as I said, you can easily also use other tools to create the signal for you. For example, simulation or so. The second question, I hope this was answering your question well, Johannes. The second question is the phantom function internally using the NUFFT with min-max interpolation for producing the k-space phantoms? No, it's actually using the Fourier representation of ellipses here. So you won't run into inverse crimes by using it. Oh yeah, well, Martin, you answered that already. Awesome. That's convenient. Yes, good. Okay, and then this was just the reply to Martin that he answered the question. Yeah, so do you have any other questions regarding the Phantom tool? I will be also present in one of the breakout rooms later, so you could also just feel free to ask me there. You can find my email address on top of the Jupyter notebook here. You can also scroll to it again, so also feel free to just contact me or the BART list if you have questions about this, the BART mailing list.
Yeah, thanks, Nick. And just again to encourage everyone, if you have questions, feel free to unmute yourself and ask or use the chat. We want this to be as useful as possible for you. So we'll give it a couple minutes and we can switch over to Xiaoqing in the meantime to get started.